Hello everyone, this is my explanation for finding the Taylor or Maclaurin series for a trigonometric function such as the cosine of x. But first, in order to do this, we need to understand what a Taylor series really is. It's about finding polynomial functions which are approximations for functions. And this is because polynomials are just easy to work with. Taylor series are largely about matching the first, second, third, fourth, and etc. order derivatives of the original function and the polynomial function. This is important, however, we also need to match the y-intercept of the graph, but we'll get to that later. Because this method uses derivatives, we need to know how the cosine of x differentiates. And this is why I've shown this little cycle here. This shows that the cosine of x differentiates to minus sine of x, and minus sine of x differentiates to minus cos of x, and minus cos of x differentiates to sine x, which once again, crucially, leads to the cos of x. This last step is very important because it means that the function can be represented as an infinite sum, because the derivatives of the functions are going to be predictable. So the exact function for cos x can be found, not just the approximation. So let's get started with this method. First, we need to find the y-intercept, and this can be represented by finding the coefficient of x to the power of 0 of our polynomial function. So at x equals 0, cos of x is equal to 1. And that means that our y-intercept is 1. That means that the coefficient of x to the 0 is 1. Now this step doesn't really use derivatives, but the next steps will. Now you can repeat this. At x equals 0, once again, f primed of x, the derivative of the function, or minus sine of x, is equal to 0. Now, 0 differentiates from 0x plus c, and this c we already know to be 1 from the previous step. So what we have so far is 0x plus 1. So that way we know that the coefficient of x to the 1 is 0. We can repeat this step further, including the second order derivative. Now at x equals 0, once again, f double primed of x, or minus cos of x, is equal to minus 1. But what does this differentiate from? Here we need to find the second antiderivative of minus 1. And that would be minus a half x squared plus bx plus c, as shown here. And that means that the coefficient of x squared is minus a half. And of course we already know the values of b and c here. B is 0, as done in the previous step, and c is 1, because that's the y-intercept that we already figured out. And once again we can repeat. At x equals 0, f triple primed of x, or sine of x, is equal to 0. And the third antiderivative of 0 is 0x cubed plus ax squared plus bx plus c, as shown here. What we're really interested in here, again, is the coefficient of x cubed, because we know a, b, and c in this scenario. The coefficient of x cubed must be 0 here. And then we can repeat one last time. You might think that we'd need to repeat an infinite amount of times to find the exact value, but because of the cycle shown above, we only need to do it 4 times. So at x equals 0, f quadruple primed of x, or simply cos x once again, is equal to 1. And what's the fourth antiderivative of 1? That would be x to the 4 over 24 plus ax cubed plus bx squared plus cx plus d. And once again we know the values of a, b, c, and d. So we have a fairly good approximation so far for the cosine of x. And once again we know now that the coefficient of x to the 4 is 1 over 24. So what we have so far is this polynomial. 1 plus 0x, or just nothing, minus x squared over 2, plus 0x cubed, plus x to the 4 over 24. Now this simplifies simply to 1 minus x squared over 2, plus x to the 4 over 24. And that can be written as x to the 0 minus x to the 0 over 1, which is 0 factorial, minus x to the 2 over 2 factorial, plus x to the 4 over 4 factorial. And because the cycle repeats, we know that this pattern will repeat. And we know, again, that factorials are going to be used, because factorials are very, very important in finding derivatives. So here we have an approximation of the cosine of x. Now the important thing to remember is that this is an approximation right now, because we haven't added all the terms yet. But as this pattern repeats due to the cycle of derivatives shown above, remember this one, the true value of the cosine of x is equal to an infinite sum, and this can be shown as this: x to the 0 over 0 factorial minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial, and so on and so forth. This is all because the derivatives are going to be predictable for the cosine of x. And this can be shown using the sigma notation for the infinite sum. Cosine of x is equal to where k equals 0 as the starting point, and going all the way up to infinity, x to the 2k all over 2k factorial
times minus 1 to the k.
The x to the 2k is important because we're starting at 0 and it's going 0, 2, 4, 6, 8 and so on. And the 2k in the factorial part of this is important as well, because we're using 0 factorial, then 2 factorial, then 4 factorial, and so on. So this proves that we can find the Taylor series of a trigonometric function, such as the cosine of x, not necessarily just as an approximation, but as the exact value. I've actually also made a program to show this. This program shows that Taylor series don't have to just be used for trigonometric functions, they can also be used for geometric functions. And this program also shows us visually how Taylor series really work. So I'll just run this program. Right now the program is trying to draw the graph on Python Turtle. This is so that the function and the polynomial can be drawn on it. Okay, this program finds the Taylor series for any geometric function in the form of c times b to the x. B is the base of the geometric function, and c is the coefficient of it. So I can represent c as an improper fraction. So the way I can do that is to write the numerator and the denominator. So I'm going to make it 1.5. So that would be 3 and 2. Now I can enter the numerator and denominator for the base, and that I can just say is 2, for example. That'd be 2 and 1. Now Turtle will draw the graph as it's shown here. This graph is green because this is the original function. And now the program is drawing the function that shows the polynomial just for the y-intercept of that graph. Next, it will match the first derivative with this function. Of course, this Taylor polynomial is 4x equals 0. So that's what it's approximating this function at. Next, it matches the second derivative, the gradient of that function. And you'll be able to slowly see that the polynomial function and the geometric function, the original one, will begin to match. They'll start to look very similar. And this is exactly why. They're matching the y-intercept, the first derivative, the second, the third, and the fourth, and so on. And eventually, if we do that an infinite number of times, you will find the actual polynomial that represents the exact geometric function here. So I've just done this, iterated this 5 times, but of course you can do it more times if you want. This is just to save time. But we can see that the first, second, third, and fourth derivatives are matched, and that's good, as well as the y-intercept, of course. So we can see this on the console. We can see that the coefficient of x to the 0 is 1.5 over 1, so that's just 1.5. And then you add 1.0397, etc. x to the 1, which is just 1, all over 1. That's just the same thing. And then you do 0.72, which is the coefficient of x squared over 2. And then the coefficient of x cubed over 3 factorial, 6. Which is approximately 0.5. And then you do the same for x to the 4 and x to the 5. This matches the Taylor polynomial for the terms x to the 0 to x to the 5. And this shows that approximations, maybe not infinite sums that will show the exact function, can still be represented using Taylor series, especially centered around a single value of x. In this case, x equals 0. So I hope you've enjoyed this demonstration of Taylor series. Thank you for watching, and yeah, thank you.